So here we are, April Fool's Day, and we are working on terrific trio and rotation problems. I hope everybody's doing well. As you can see, I figured out how to change the brightness on my camera, and you guys will have to determine whether or not that's a good idea or a bad idea. But I guess we got to kind of get down to it. So I posted the first link on here was to some notes that I had already done in class. Oh, what are my glasses? I had already done these in class, but I hadn't actually attached the sheet, which is the relationship between linear and angular quantities. So here we have our linear values, D, V, and A, and the terrific trio formula. And then down below, beside that, we have the angular quantities, theta, omega, and alpha, and then the terrific trio formulas. And then the fourth one there is something that seems to come into play a lot in these problems, which is the average velocity would be if you take the final velocity plus the initial and divide by 2. If you have a constant rate of acceleration, that works. The same thing is true for angular quantities. So if we have omega average equals the final plus the initial angular velocity divided by 2. So here we go. We are going to do the third page in this rotation packet. It's actually the first set of problems we're going to do from it. And we're going to do the front and back of this. So push pause if you don't have this out. Push pause and grab it. If you do have it out, buckle up. Here we go. So number 1 says, an immersion blender boasts that its blade travels at 1,200 RPMs. RPMs. Huh. Well, first of all, what the heck's an immersion blender? Well, just so happens that I have one down in the kitchen. So I got it right here. That's an immersion blender, and they spin really fast. Don't stick your finger or your tongue in there. That would be bad. So that is an immersion blender. See how it spins? Yeah, that's the highlight for the day, guys. Now, no, that could have been the highlight. An immersion blender boasts that its blade travels at 1,200 RPMs. All right, here we go now. RPMs. I know you already know what it is, but I'll pretend like you don't. RPMs is going to be the revolutions per minute. Oh yeah, that's exactly what the word says, revolutions per minute. Here's the thing. This is actually a measurement of frequency, because it's how many revolutions per unit time. It just has different units on it. So if I have 1,200 RPMs, and I rewrite that as 1,200 revolutions per 1 minute, I know I could leave the 1 out. Oh, you guys are so smart. Now I'm going to put minutes on the top and seconds on the bottom. And when I look at my conversion factor, I'm going to have 1 minute divided by 60 seconds. What is 1 minute divided by 60 seconds? That's right. 1, because they're the same thing. Dimensional analysis. So 1,200 divided by 60, I think that's going to give me 20, is it not? So 20 revolutions per second, which we call hertz. So A says, what is the frequency? B says, what is the average angular velocity when traveling at this speed? Well, the average angular velocity, so omega, is going to be 2 pi times the frequency, or 2 pi over the period. And this is true when it's traveling at a constant speed. Oh, well, I might as well use the 2 pi times the frequency one, right? That's easy. 2 pi times 20. That's right, that's going to be equal to 40 pi radians per second. Technically, I could just leave that as hertz, because the radians, as we saw earlier this week, is sort of a unitless value. But I'm going to leave it on there because I think it solidifies. It helps us see it. If I actually multiply out 40 times pi. If I wanted that in a decimal form, I would end up with 126 radians per second. All right. Easy so far. Now, the switch is turned off, and it takes 3 seconds to come to rest. What is the angular acceleration during this time? All right, so here it goes. I can't just plug into this formula for omega because the velocity is changing. So I need to use terrific trios. I'm going to do the same exact process I've always done, which is write out the variables. Omega naught plus omega, alpha, theta, t. I know that takes longer for you to get to because you haven't done it before. That's all right. No worries. Now, this initial angular velocity is going to be the 40 pi radians per second. The final angular velocity is 0. Alpha is what I'm looking for, and the time said it was 3 seconds. So what formula do I know that doesn't have theta in it? Oh, that's right. Now, here's the thing. I make this look too easy. Honestly, if you have to do this, you can. You say, oh, yeah, that's the formula without D. And then you translate it right down below. In my mind, at the beginning of this unit, every year, I still kind of translate it in my head. No, so we're looking for alpha. So omega minus omega naught divided by t equals alpha. Yes, I could have just crossed off the omega naught. I'm sorry, the omega. My bad. So I get minus 40 pi divided by 3. And I get an angular acceleration of negative 41.9 radians per second squared. Now, I also could have left that as negative 40 thirds. I could have times pi, but I put it in a decimal. Check. All right, so that's C. Oh, there's 2 more parts. What is the angular distance the blade traveled in this time? Oh, so now we're just back to utilizing terrific trio again. I've already made a chart, so this is pretty easy. I think I might use the formula that's already solved up for theta. Theta equals omega naught t plus 1/2 alpha times squared. Now, how did I do that? Brilliant. But really in my head, I'm saying D equals V naught t plus 1/2 a t squared. And then I translated it. This is like Spanish 2, guys. We're moving up here. Spanish dos, excuse me. So if I solve it up for theta, I'm going to have theta equals 40 pi times 3 seconds plus 1/2 times the negative 41.9 times 3 squared. If we translate this into English, this first part right here, that's the distance it would have traveled if it didn't slow down. This is how much distance less it travels, angular distance it travels, because it's slowing down. Yeah. I plug them in. I get an answer. I'm going to wait for you guys for the moment. Get your You don't even have your calculators out yet. It's brutal. Oh, did you get 188.4 radians? Probably should leave that as 188. All right. Lastly, if the radius of the blade is 2.5 centimeters, what linear distance did the blade tip travel in that 3 seconds? This is where I go to my conversion. Now, right here, it says D equals R theta. And that makes sense, I hope, because it goes back to the arc length formula. S equals R theta. So whatever the angle was it traced down, times the radius, gives you the linear distance. Now, 188 radians means it went around a whole ton of times. Did you see the blender? Of course it went around a lot. It still went around a lot while slowing down. So, let's plug it in. A, B, C, D, E is going to be D equals R theta, 0.025 meters times this angle, 188.4, and it traveled a linear distance of 4.71 meters. Check. Back. All right, good. So the next problem has a drag racing car from New England Dragway. So I found this footage. You ready? It's nuts.
The National Hot Rod Association tours the country, making several stops throughout the year. Every summer, fans fill the New England Dragway in Epping for a front row seat to the action and some up-close and personal time with the drivers. We've got a car that's...
All right, I think we'll stop there. Let's go to the problem. Ready? Flip it over. Here we go. At the New England Dragway, modified cars running on jet fuel can complete the 250-meter straight course in 3.2 seconds. That is ridiculous. Assuming no slipping of the 0.75 meter radius tires. Now that's a big assumption there. It is. Roll with it. All right. And that the car accelerates evenly for the entire trip. Again, kind of a big assumption. A, what is the final angular velocity of the wheel? What is the angular acceleration? And what angular distance did the rear wheel travel during this race? Now here's the best part. I'm filming this. I still don't know how to edit these well. So we've got to figure it out as we go. So what do I do when I'm not sure? That's right. I draw a picture and stall. So here's a car. I think they have small tires in the front, big tires in the back. Yeah, something like this. It probably has a spoiler on it, another wheel in the back, and boom. All right. So we just watched that video. What was the initial velocity of that cart? 0. Yeah, that's right. Good. It completes the track, which has a linear distance of 250 meters in a time of 3.2 seconds. All right. Is there a formula that I can utilize to solve for either the acceleration or, I'm going to take a slightly different approach. You ready? Here we go. The average velocity is going to be the final velocity plus the initial divided by 2. Oh, the average velocity is also just going to be the change in distance over change in time. So the average velocity is 250 meters divided by 3.2 seconds. Wait a minute, that's like elementary school physics. Take the distance divided by the time and gives you a velocity? Yeah, that gives me 78.1 meters per second. But that's the average velocity. So if I'm making my list here, how could I solve for the final velocity? Because then maybe if I know that, I can find the final angular. Oh, I could plug it in here, couldn't I? I could say that since the average velocity is the final plus the initial divided by 2, the initial velocity, since it started at rest, is 0. And I'm going to say twice the initial velocity, twice the final velocity is equal. Oh, sorry, I didn't mean for you guys to have to see that. Twice the average velocity is going to be equal to the final. So 2 times 78.1 equals the final velocity, which is going to be 156.25 meters per second. Could I have done that another way? Of course I could have. You always can with these terrific trio. So what am I trying to find again? Oh yeah, what is the final angular velocity? Well, to find the final angular velocity, the relationship I know between linear and angular is v equals r omega. So if I do v divided by r equals omega, I can take that 156 meters per second and divide that by 0.75 meters for the radius. And I get 208 radians per second. All right. B, what is the angular acceleration? I could do this a few different ways yet again. I think this time I'm going to do this. If the initial angular velocity is 0 and the final angular velocity is 208 radians per second, and the time is 3.2 seconds, can I solve for alpha? Heck yeah, that's pretty easy, right? I can say omega equals omega naught plus alpha t. Omega naught cancels out. Yeah, you still with me? So omega divided by t equals the acceleration. So 208 divided by 3.2 equals 65 radians per second squared. I could explain that a couple different ways, but then it just gets more confusing. If you thought of another way to do it, I bet it's better because you thought of it. C, what's the angular distance? What angular distance did the rear wheel travel during this race? All right. Well, I could again do terrific trio if I wanted. I've got omega naught, omega. I know some of you right now are screaming at the screen, saying, don't do it, Mr. Edgar. You don't have to do all that work. I know, but I want to. Theta equals question mark. So I might say theta equals omega naught t plus 1/2 alpha t squared. That's ugly. I know. That goes away. End up with theta equals 1/2 times 65 times 3.2 squared. And I've got 333-ish radians. Now, I also could have just said D equals r theta, and since it traveled 250 meters, 0.75 is the radius. You know what you get? 333 radians. Check, check. Hope you guys are doing well. I hope this stuff isn't killing you. I know you still don't feel comfortable with the letters. Relax, you'll get it. You didn't feel comfortable with any of this stuff in physics when we first started. Heck, if I just showed you this worksheet, you'd be blown away. But now you see the work on it and you're like, oh, I get that. I totally get that. Okay? You guys can do it. You follow the same steps we always have, and you just work through. Anyways, hope you guys are good. I'm going to push stop here and call it a day on this record. You could always check out New England drag racing too. I've never been there. I've heard it's nuts.